Okay, so I guess let's start. So welcome everybody to our next OWPS probability seminar, last one for this year, 2 more to go in this term after this one. So it's a great pleasure to have today Patrik Ferrari from the University of Bonn and Alessandra Occelli from University of Angers. We're going to speak about last passage percolation models on the half space. So Patrik is going to start, so stage is yours.
Okay, thank you, Dominic and Peter, to invite us to give this talk. First, I will say something about last passage percolation. I will start with full space and I go later to half space. So what is the last passage percolation in full space, first of all? I start with one case, the simplest case possible. You consider, like in this picture, this dot, for ij positive, you put some IID geometric random variable with parameter q, say q between 0 and 1, and then the point-to-point last passage percolation for one point that I call 1, 1 to mn. What you do, you look all possible paths which are up and right that connect 1, 1 to mn, and you sum the random variable that you see along the path. And then if you maximize over all possible paths, this is the so-called last passage percolation. Okay, this is a very, there is nothing about dynamics at this point. But if you take the limit when q goes to 1 of the random variable and you multiply by 1 minus q, so this, when you take q going to 1, this random variable becomes very, very large because the average is 1 over 1 minus q. So if you multiply by 1 minus q, this remains bounded. And indeed, this random variable, you know from probability 1 that they become exponential random variables. So the exponential last passage percolation correspond to take the omega ij to be just IID exponential distributed, say with parameter 1 for the moment. Now, there is a well-known connection between the so-called totally asymmetric simple exclusion process, if you have seen this model already. This is an interacting particle system and the last passage percolation. And this is that if you start with a so-called step initial condition, so when you have the particle xn of t is the position of the nth particle at time t, counted from the right, so and they start all as a block. Then there is the last passage percolation to mn is less than t, exactly when the nth particle already made m minus n jump. Already made m jump, which means it's a position greater than m minus n. So in this talk, we will speak in particular about the stationary last passage percolation. At least one of the stationary measures for last passage percolation is the following. So if you fix a parameter now between minus 1/2 and 1/2, and then now you do the following modification. You add a column and a row here. So at I equal to j equal to 0, you add 0. The random variable is 0. Otherwise, here you add some random variable which are exponentially distributed with parameter 1/2 minus alpha, and here 1/2 plus alpha. Then this is so-called the stationary last passage percolation. So this stationary last passage percolation is very well known to be stationary, and also the name is coming from that because of the following property that Martin, that was online before, and with Catherine and Timo obtained in a paper. So if you look here, the increment of the last passage percolation on the first of the zeros row is just the difference between the sum of the random variable, which we are exponentially distributed with parameter 1/2 minus alpha. Now, the fact that if you look at a different level, say at level n, And then look at the increment of the last passage percolation. Now this will also be IID random variable with the same law as before. And similarly by symmetry also in the vertical line. And actually even on any lines we go down right line. So this is the reason why this is called a stationary last passage percolation. Now, if you start with this model, the geometric LPP, there is, however, another connection, another limit, which is very natural and will be also the content of the second part of the talk, so the one by Alessandra, is the limit when Q goes to 0. So you think that you have Mn, these are integer, and suppose that Mn scale like x over square root of Q and y over square root of Q. So which means say x and y are finite, but then you take Q going to 0. So for most of the, for say fixed x and y, for all ij less than Mn, so I less than M and j less than n, most of the omega ij will be simply 0 in the limit. But then once in a while, there is the omega ij will take value 1, and this, because of this scaling, will have a positive fraction. So the number of omega ij for ij less than Mn will be of order 1. And in the limit, when Q goes to 0, none of the omega ij will have value more than 1. So one can then represent just as a dot, just the omega ij which take value 1 and nothing else. And then if you think that x and y are fixed, and then you take limit Q goes to 0, this is the so-called Poissonized version of the LPP, also Hammer's-Lay process. So here you can see what you have here. You have simply a Poisson process with a given intensity, 1 or 2, depending a little bit how you scale. And then the last passage percolation was the sum of the omega ij that you see. But now the omega ij, here are all essentially 0, except for some which are 1, which means what you have here, you start from 0, 0, and then you try to collect the largest number of points that are the omega j, which take value 1. And the path has to have a slope between 0 and infinity, so going upwards. So here you see there are several lines, and this is typically, so the path, the way to collect the most number of points is not unique. In general, in the exponential LPP, it is unique, but in the geometric or in this Poisson is not the case. And this is also called the Poisson LPP. Now, why this is interesting for us is because there is a tight relation with the so-called Carter-Perzich-Chang universality class of stochastic gross model. So the picture, so this one have to say that this kind of, for the point-to-point problem, for example, the fact that the longest increasing subsequence, because you can think that these points you can parameterize by a random permutation for a random length. And by Johansson indeed proved that the limiting distribution of the number of points which are seen when your x and y goes to infinity convert to the so-called Tracy-Widon distribution. And then also in some other situation I will mention. But now, more or less at the same time, Perot and Spohn, because Herbert knew that the polynuclear gross model that was already defined in physics, notice that this model is nothing else than a 45 rotation of the so-called polynuclear gross model. So the right-hand side is the last passage percolation. So here there are lines, and this region are the one that you can reach with touching 0 lines. At the most number of points that you can collect here is 0. And this intermediate point is 1. here is 2, 3, and 4. So if you rotate the picture by 45 degrees, you see this picture here. It's just a rotation, and the point is that the number of points which are seen below a position x on t is called the height function of the polynuclear cross model. I will show you how does it look like in a moment. So you can think that the polynuclear cross model as the height function will be some piece like that, piecewise constant with jump. The jump will be exactly at, if you think at a fixed time, you take a horizontal axis. So the up and down jump correspond to the position of these lines. And what happens in the dynamics, simply the down jump, they move to the right with speed 1, the up jump to the left. And then when there is a point, that is a new Poisson point, this is a nucleation, which means there is a creation of an up and down jump, which then starts spreading. And I want to show you how it looks like. So this is a simulation. So here you see not exactly a Poisson process, but I fixed the number of points to 200, for example, but it's very similar to a Poisson process. So you have uniformly distributed 200 points. And this red line is the height function. And when I let it run, you will see what is going to happen. So every time that there is here there was a Poisson point, and here there was a creation of the up and down jump that start spreading. And when these two comes together, there will be a annihilation. So there is a smoothing mechanism coming from the fact that the island tend to merge. There is some local randomness. And this model belongs to the so-called Carda-Parsit-Sang universale class of cross model. And make it even larger, faster if you want. If you want, you can go backwards. Yeah, I should change. Okay, it's not working anymore. Oh, exactly. To go backwards, you can do with a trick because you have to save a little bit more information. Oh, this. Now, there is one version that will be mentioned by Alessandra, but I will not say too much. You can also think that at the boundary here, you add some extra point, some Poisson point with some density. Then the picture looks a bit different because at the boundary, you can have a lot of nucleation that push up everything. So you can imagine that the distribution here will be different, will be something different. And using appropriate boundary condition, you can also get to stationary situation. Now, I would like to mention two of the limiting distribution which are known in the full space. One is the point-to-point last passage percolation. So here is in the case of the exponential LPP. So last passage percolation to the point NN as law of large number 4, so it's about 4 times n, the value, and fluctuation of order n to the 1/3, and the law is given asymptotically by the Tracy-Widon distribution for Hermitian matrices, the so-called GUE Tracy-Widon distribution. And this has different expression. One expression is the one given in terms of a so-called Fredholm determinant of the Airy kernel. And the second limiting that I want to mention is the stationary initial condition correspond to take alpha equal. So here, okay, here we look at a point in there around the diagonal. And if in order to see something non-trivial, we take alpha essentially 0 for simplicity, but every other alpha can be also made. And then by Morales obtained actually first in the geometric and in the Poisson case, that the stationary case, the limiting distribution, if you look at point of order n to the 2/3 away from the diagonal, the limiting distribution is non-trivial and is given by the so-called bike-range distribution, and W is actually a family of distribution function. W is the parameter tell you how far you are from the diagonal. So the structure of this bike-range distribution is the following. There is a derivative. This is just the one-point distribution like in the step, in the point-to-point case, and times some other function. This you don't have to read precisely, just to mention that the function g is explicitly known. The function g is, there will be some explicit function, some whatever. A are some array function, the other are just exponential, integral of exponential, and so on. And this one is just the inverse of the operator, which define the Freidon determinant of this operator is this trapezoidal distribution. So the structure is the following. There is some strange derivative that one could say very strange. This itself is a distribution function times some extra other stuff. So before going to the half space, I want to explain you shortly in this setting how this structure arises. So to obtain this formula, one starts with an integrable model. So we have different boundary conditions. We have here on this side exponentially random variable is parameter 1/2 plus alpha. Here 1/2 plus alpha. Here 1. But then we add at 0 an exponential random variable parameter alpha plus beta. So this should not be there for the stationary case. This we call tau, this random variable. But if you have alpha a beta satisfying alpha plus beta positive, otherwise the random variable is not well defined, then this can be described in terms of so-called Schur process. And using the Schur process, one gets an explicit expression for the last passage percolation in this setting with this extra tau, and this is given by some Freidon determinant for some given kernel. So what we want to look is actually is this random variable subtracting the tau because we don't want it, but then we have to take the limit beta plus alpha goes to 0 or beta goes to minus alpha. This is what we want to do. Now the derivative comes from this shift argument. If you try to compute this distribution, you find as the following identity. So if you want to prove yourself, you just write down the Laplace transform of this random variable, and then you will relate with Laplace transform of this one. And in the way you will get this factor in front. So you see, okay, there is a 1 here, but this there is 1 divided alpha plus beta. So if the term with the derivative remains, means that the term here, essentially this quantity should go to 0 linearly in alpha plus beta in order to cancel this. So if this doesn't happen, then it's not likely that something happens. But if this goes to 0 linearly in alpha plus beta, this one disappears in the limit. This is the reason why in the end you get a simple derivative of something. So the next step is that K itself can be written like the kernel without the boundary condition plus alpha plus beta times a function of x times function of y. So this is a rank 1 operator. This is just a full rank. So using this, you can write the Freidon determinant like the determinant of 1 minus k bar times this quantity. This is done. So in principle, this one is actually the determinant of 1 minus 1 minus k to the minus 1 applied to f of x times g of y. But then this is rank 1, which is a determinant of a rank 1 is just a single scalar product. But the point is that you get this nice expression. So what we want to consider is this quantity, the limit beta goes to minus alpha, the derivative of this bunch of stuff. And we still have this 1 divided 1 plus alpha that is annoying a bit. But the idea is just to expand this 1 minus k to the minus 1, like the identity, plus 1 minus k to the minus 1 times k. And the term with the identity is something very explicit. And this one is an elementary computation to see that is analytic. And the 1 divided alpha plus beta goes to disappear exactly. So after this step, you are essentially done up to some analytic work, more standard. So one shows that this kappa bar converge to this one with some bound properly so that the scalar product converge. This one will converge to the R, and this kappa bar F converge to the phi and the other to phi. So the structure is this one. So I made this kind of a bit technical part now because in the spool space, the strategy is exactly the same. There is some tricky stuff, but it's exactly the same, the philosophy. Now let's look at the half space. What is the LPP in half space? So if you go back to this picture, so how would you define something in half space here? Half space would be, this is x, and this is kind of time. These are the position of the nucleation. So it would mean that the nucleation should be only in half space on one-sided. What you can also put is, if you want, some put at the x equal to 0 is a boundary of our system. You could also put some extra nucleation if you want. This is even more natural if you think in, if you have the picture in terms of the exclusion process. So in the LPP, half space corresponds to the following setting, very similar to before, except that the stationary half space, you put exponential 1/2 plus alpha on the diagonal, not on the vertical line. And this, otherwise, the setting on the definition of the last LPP is the same. You start looking all the paths, starting from this point to the end point, that go right on up, and you collect the maximum number of weight. Now so this is the definition, as I said, is exactly the same. Don't have to change your mind setting, just that the variable here are different. So for example, if you would think at the full space analog, this red one would be here. Then this one, what is this? You can think that is the increment of the last passage percolation from this point to this one. And this is the increment from this to this. Now this increment, if you are in the full space, they are not at all, they have the same law, but they are not, so point y, each single variable, but they are not at all independent. So in this setting, they are really independent. Now we can look at the following case. So this is 1/2, so the diagonal is 1/2 plus alpha. So the average is 1/2, 1/1/2 plus alpha. For alpha equal to 0, the average of the exponential is 2. If alpha is less than 0, it's even larger. So if alpha less than 0, you have typically on the diagonal large weight. And typically, if you look at this kind of picture and you try to understand which points are non-trivially correlated, it turns out they are on so-called characteristic line. And this F in this MN slope, these have a given slope, or this slope. Now for alpha less than 1, then 0, the slope are like that. You see this one. So the slope is smaller than 1. So which means the points which are non-trivial correlated are close to one of these lines up, and the fluctuation will be of order n to the 2/3. So if you look, for example, which position is non-trivially correlated with the origin, naturally would be one point that is essentially like that, so it's far away from the diagonal. So in this case, you will see the origin a little bit at the beginning, some random, you see the weight here a little bit at the beginning, but eventually you don't see many of them. On the other hand, if you take the end point to be on the diagonal, the paths which tend to maximize the last passage percolation, these are also called geodesic, they will tend to follow this going backwards, tend to follow this line. So will be pushed all the time toward the boundary, which means, at least it's not, we did not try to prove, but heuristically it will typically see order 1 random variable on the diagonal, which are random variable which the higher, they have a higher expectation as usual, as the one in the bulk. So if you see a lot of them and they are all independent, it's not so strange to guess that you might have some Gaussian fluctuation on the order of square root of their number. So indeed, if you take a point here, for alpha less than 0, you will see just Gaussian fluctuation on the order square root of n. So the other case is when alpha is more than 0. Now the line where there is a non-trivial correlation f slope which goes away from the diagonal, but then even if you start at the diagonal, this maximizer will touch the horizontal line here at a distance of order n, and after that they have to go back to 0, and they have here is really a sum of IID random variable, and you have order n of them. So you also get Gaussian fluctuation of order square root of n. So in order to see something non-trivial, then we have to take alpha close to 0. Otherwise, you see just Gaussian. So you might be interested, but to say, okay, maybe it's not so interesting. So what we take alpha like delta, say n minus 1/3, and we take the endpoint also at that distance n to the 2/3 from the diagonal. So n would be the diagonal, and subtract eta times n. So eta scale like n to the minus 1/3. So this is like minus u n to the 2/3. So we take alpha like that. The 2 to minus some power, can forget about, they are not important. And then, so the law of large numbers, since it's stationary, we know what it is because the expected value is the sum of, so the increment are, we know exactly the distribution. So the increment here are exponential with parameter 1/2 plus alpha, and the increment horizontally are exponential 1/2 minus alpha. In the stationary case, then we can compute explicitly the law of large, the expectation of this is up to order n to the 1/3 is this explicit quantity. Now, since we expect actually that the fluctuation of the last passage percolation goes to infinity like n to the power 1/3, if you want to write a scaling limit, we should at least subtract this term. Whether we subtract this term or not is a choice. So since the formula were looking a bit nicer without subtracting, we decided not to do. So here you see, we subtracted only the first 2 order, not the last one. And what we found with Alessandra is that the limiting law of the last passage percolation close to the with critical parameter convert to a well-defined limiting distribution And the structure of this limiting distribution is similar to the structure of the bike range distribution, except that, okay, there is a derivative. Here, instead of determinant, you have a Pfaffian, okay? But this is nothing else than really the problem without the boundary term. So if you take alpha, if you go in this situation, you remove these colored lines, then what you get exactly this object times another term. And this term is some function minus a scalar product where you have the inverse of this object. The only difference is, the main difference is that here, instead of a determinant, we have a Pfaffian. Instead of a scalar kernel, we have everything have a 2x2 matrix structure. And this is what I said. So the alpha I bar is the one, this was obtained first away from the diagonal by Imamura Sasimoto, and then fully rigorously also in terms of process later by Jinho, Guillaume, and Ivan, and Tufik in 2018. Now this formula looks very bad. Suppose that you want to put in a computer, you say, oh, what do I do? Now, okay, the Pfaffian is you can think square root of a determinant. Okay, determinant is not so bad. There are some way of doing it. But now they have a derivative and they have this inverse. So these are all stuff which are not problematic. If you compute the moments, for example, the expected value, you don't have to use the computer, you know by analytically that is given by this quantity. So if you look higher moment, you just integrate by part. So if you have this one is the derivative of something t, then you can just integrate by parts and you have everything written in terms of t. Okay, now t was this bad stuff. Pfaffian, okay, so you think at the terminal, but then you have this resolvent. How do you do? Simply, this is a short way of writing of the following stuff. So there is an identity that came from the determinant analog in a paper of, I knew from Sasimoto in a paper. So this identity can be written as a linear combination of two Pfaffian, which are square root of determinant. And determinant can be numerically very well computed as soon as the entries, the kernel are analytic, is the case in our case, by a program built up by Bornemann 15 years ago, more or less. So numerically, this is not really an issue. This is the compact way to writing. If you don't like this inverse, you have to write a diff. You replace the term with this one as a different of two paths, and everything is fine. Now, historically, the first result was the point-to-point last passage percolation was obtained by Bacon Rains, where they used then some result on, they added also some, actually they were looking at permutation and they put some symmetry on the permutation, they all obtained other object. This is what I already mentioned. And more recently, there were analog result on term of half-space KPZ equation, or the half-space stationary limit that was also a work with Alessandra and Dan. Just to mention that actually stationary measure, I was putting something under the carpet because these are not all the stationary measure. Are all the stationary measure where you have IID entries in the LPP, but there is the class of stationary measure is a little bit, there is something more. There is a paper on Guillaume and Ivan which treat this one. And recently there is in the world of TASIB a very nice paper by Shang, in which one sees how to adapt to different a space TASIB with general initial condition. There are several other results like large deviation, lower tail, time correlation, which I don't enter in the detail, but which are also available or partially available for the half space. Now here we want to compare shortly the full space with respect to the half space. So in the full space, we had the bike range distribution. It was a one parameter family. That was a W parameter which tell you how far are you from the diagonal. Here we have a two parameter family. So you have one parameter tell you, say, how far you are from the diagonal, and one is the strength on the diagonal. There are two parameters. So in the full space, everything is written in terms of determinant or random determinant. And here we have a Pfaffian structure instead, which is slightly more complicated, but still, from random metrics point of view, is still standard. Say. So it's more complicated to work, but in principle. In the full space, the analytic continuation was relatively simple to find out, at least for the one point. And for us space, it has been a bit more tricky, but this was from a technical point of view. In the picture I showed before, in this one, so suppose that you look at this case. Let me see. Oh, okay, this is the alpha, how it was scaled. So alpha is essentially delta up to some scaling. So look, if you take alpha less than 0 and I point non-trivially correlated along the characteristics, eh? Now this is very far on the diagonal. I claim that essentially in this case you should not see the effect of the diagonal asymptotically. So which means even if you are in this setting, taking appropriate limit, we should be able to recover the bike range distribution. So because if you go far away from the boundary system, the boundary you will not see anymore. And indeed, this is actually possible. It's relatively easy when you have the formula. So if you take delta goes to minus infinity, correspond to the alpha very negative, because alpha was proportional to delta. Then indeed, so here we have to, the point S where we look, we have to adapt and correct a little bit because we did not send, this function was defined to have mean non-zero. This has mean 0 by construction, and this, so this is just taking care of the mean that is again 0. And then U is the place where you look. You have also to change accordingly because U is the essentially in this picture, U give you the distance in this direction. So if delta becomes very negative, U become larger. So you want to focus around the characteristic again. And then indeed, you in the limit when delta goes to minus infinity, you recover as expected the bike range distribution function. Okay. In the last maybe 5 minutes, I want to mention a little bit how does it work? What are the main difference with respect to the full space? So first of all, we use the result of a bike-Barakan curve in Sweden, which described the following situation where the exponential 1/2 plus beta, 1/2 plus alpha, and here exponential alpha plus beta. In this case, the last passage percolation can be written in terms of not a determinant, not a Schur process, by a so-called Pfaffian Schur process. So one get for any alpha plus beta positive an explicit expression for the last passage percolation in half space. Next is the shift argument that is one-to-one with the full space. There is no difference, exactly no difference. So you get the derivative exactly. This was really for free. But now this becomes a bit more tricky. Not so bad, but slightly more tricky. The kernel has also a rank 1 type perturbation, but now everything is written in this formula, with vector everything is a 2 by 2 matrix. Before was a 1 by 1 matrix. But notice that the difficulty in the analytic continuation was coming that this function is exponential minus beta x, and say alpha positive, we want to take beta becomes negative. So this function will diverge very fast. This actually generated quite some problem. But then what we have the same structure as before, exactly the same structure. And for the analytic continuation, we expanded first 1 minus the resolvent by doing the first step expansion. Then you get this one. This term was very nice, no problem. But now this one was problematic. In particular, assume that you can expand to infinity the geometric series. Then the first term is g y g bar x, and this is actually a sum of 4 terms. So each one is diverging when beta becomes negative. They are ill-defined, but it turns out that we can modify this one by essentially removing all these terms with the exponential beta and give it the same scalar product. And at this point, we are happy because then you just apply the standard last passage, large time asymptotic, and then you get exactly what you want. Maybe since I have time, I wanted to shortly mention, oh, it disappeared for a moment. I could, oh, if the mouse is not, let me close this one, is slowing down my computer a lot. For the connection with the exclusion process, I might show you shortly an animation that is on my homepage. If it's opening, looks almost frozen. You will come. So for the exclusion process, the connection is, you have some height function, and here are particle position. This is the step initial condition I mentioned. And when one particle goes to the right, here the small valley becomes a small mountain. If you let it run, it grows. Now, what does it mean for half space to be in the half space? What would change in the half space? What would change is that you don't start with this particle configuration, but instead of all the stuff, at the origin, you put a reservoir. The reservoir put particle inside the given rate. So this is why it makes sense. And the fact that you put particle inside with a given rate happens independently. So the trial are independently. As soon as there is an empty space, the waiting time is independent of everything. And this is the reason why in the term, this is the reason why here we put exponential with some parameter, because these are actually the waiting time of the particle to enter the system once they are allowed at the origin. And with this, I'm more or less finished with what I think I'm finished with what I wanted to present. If you have questions, you are free to ask. Otherwise,
yeah. Thanks, Patrik, for a very nice talk. So indeed, we have time for questions. So as usual, feel free to unmute yourself or raise your hand if you want to ask a question. I think otherwise, let me maybe start with one already. So as soon as somehow you talk about the case of stationary lost passage percolation, at least from the particle point of view, there should be Burke's property involved. Is this like always the case? Because you also mentioned that there are some maybe like stationary systems with non-IID setup.
Yes, this is exactly, so this is essentially Burke's property. The fact that you put this waiting time to be exponential 1/2 minus alpha. There is so essentially, you can think that initially stationary, you can think that initially you have Bernoulli in the TASEP, you have Bernoulli with a given density. Bernoulli run occupation variable with a given density. By Burke's property, this would mean that if you start from the first particle in the system, then you can remove all particles to the right by changing the rate of this single particle. Now, if you apply Burke directly, then you would actually get here a finite random number of zeros, and then this exponential 1/2 minus alpha. If you would map directly to the TASEP for the stationary TASEP in half space. And so there is a small difference because here you don't have the zeros, but okay, except for this is exactly Burke property. Now the second point you ask, so the connection, there is a system of, so the stationary measures which were obtained by Guillaume and Ivan, essentially is a system where in the bulk is essentially the same, but then the first two lines are not just, this is not just exponential 1/2 minus alpha, but you have the first two lines which are a little bit special. I don't want to write down this. And this is related to the fact that was already known in Liggett, that if you have the half space stationary measure, there is one case where you have Bernoulli product measure is exactly this one, and the other cases where you have only asymptotically Bernoulli product measure. And these are the other case that Ivan and Guillaume considered as well.
Is it known that that's all? Or could there be even more?
I think there will be more for this space. But I don't know if it is proven. It's a different question. So in some sense that asymptotically will be 1/2, this kind of, this the result, this Liggett result, but it was not characterized the approach. So what was the distribution was not given in the Liggett work. I don't know if there is a formal proof that they are the full one. Not quite sure.
Also not quite sure. Yeah. Okay, any further questions? So feel free to unmute yourself. Yeah, Peter.
Just one much more naive question. So at the beginning, you sort of gave the connection of this very discrete model with sort of the limit Poisson process version, and then you went to the half space and so on. So and you gave a list of results that exist in one form or another. So how much of that can then be actually brought further to this sort of Poisson version of the model? Because I got the feeling that a lot of those are very much still lattice-based statements, right?
You mean this one?
Yes, I think here you were talking about.
Okay, this one was in Poisson already.
Yeah.
This one, in principle, when you have the Schur system, it should be possible to do. So in principle, every point could be made also for the process and so on, but has not been worked out precisely for the Poisson. This is also what Alessandra will speak about in the next part for the stationary case. They are working to, because also the formulation that kind of the formula that Pike and Reins obtained, they were not the Fredholm the one I showed you. They had different formula. They had formula related to some solution of some Paine-Levé and so on. They were alternative formulation that you will also kind of see in the second talk. But in principle, it should be possible to do everything also in the Poisson. So if you want to stay in the Pfaffian picture, it's just what is not written down is just a question of sitting down, writing down. However, what is not trivial is to see what is the, for example, what will be the limiting. So what kind of formula you will get not in terms of Fredholm, Pfaffi, and so on, but more in terms of the original work of Bacon Rain. But this I don't say anything more, otherwise Alessandra will kill me.
Okay, thank you.
Thanks. So any more questions? Doesn't seem to be the case. So thanks again, Patrik. And I think we can maybe do like a 3-minute break and continue then 5 minutes to the hour.
Okay.
Yeah, nice. So Alessandra, you're oh, you maybe wanna, oh, you're still muted. So
Sorry. No, I was saying that maybe I can start sharing the screen so that
exactly, just what we have is we use the time to make a smooth transition.
don't look at the mess on my desktop. Okay.
We'll cut it out later on. The YouTube. No worries.
Yeah.
But let's maybe indeed wait like 2 minutes. So typically it's good to have like a short break between the talks. Maybe Patrik, it was I hope it was fun. I just posted the link to your webpage on the Zoom. So yeah.
The webpage should be
So people can try I guess
so yes, actually this animation they are there, but they were written in Java applet, so you will not be able to open except if you use Java. They use. It was funny because last I asked Reminic to tell me how he managed to make my animation working again. This applet viewer, but this is actually working not with the last version of Java that was produced, but the previous one, the 8. If you have the last one in online, it will not work. You have to install the old one. Because of security reason, they stopped doing this. But of course, if you write yourself your stuff, you know that you don't have problem.
But you also have the JavaScript versions and they
The
still work, right?
ASEP, I have the JavaScript version. The PNG, not. I did not have time and energy to do it. Maybe someone want to do.
You can ask a student, maybe, for some project.
Motivate a student.
Yeah, all right. So, yeah, maybe then let's return. So welcome everybody back for part 2 by Alessandra. And she's going to talk about the PNG model in the half space. So Alessandra, here you go.
Okay, thank you. So as Patrik briefly announced, I'm gonna give a different description of this polynomial growth model in half space. I will explain why this formulation that I will present is slightly more convenient in some context. So the setting might look the same. I cannot move. Okay, now I can change slide. I mean, the setting is quite the same, but actually the techniques and the object that I will present differ quite a lot. So the starting point is always the political growth model, which here is actually, this setting could be known better as the Hammersley last pass speculation model. I decided to call it PNG because of historical reasons. So everything I will say is set in the terminology and the notation of 3 papers written by Beck-Rains in 2000-2001 that deals actually with the problem of studying this model with different symmetries. So the setting is, so the model is the following. So we have a unit square and we generate a random subset via a Poisson process of intensity t squared. And then you add also Poisson distributed points on the horizontal and the vertical side. So one with the alpha, with parameter alpha plus t, and the other with the parameter alpha minus t. And then you look always at the path, the directed path that collects the highest number of points. So and you define L to be its length. And this, as Patrik mentioned, so L of t corresponds to the height function at position 0 of the polynuclear growth model when you add boundary nucleation events. So the case where the boundary parameters are 0 is of particular interest, and it has been studied in different settings. And basically what happens is that, well, you don't have any more boundary events, boundary nucleation events. And so this corresponds to the classical model for, this can be mapped to a model of random permutations, where basically you can associate, you can see a permutation by associating the taking at each point and associating the y coordinate relative to the x coordinate. And so basically L of t will correspond to the length of the longest discrete subsequence in this random permutation. So here, for example, if I counted well, this should be the corresponding increased subsequence that corresponds to the longest path. And for this model, it was proved that the fluctuation of the lengths are described. So they are, first of all, the statistics, they are the same as the models in the KPZ universality class, and the fluctuations are described by the GOE Tracy-Widom distribution. So they are the same as the fluctuation of the largest eigenvalue in a Gaussian unitary matrix. Okay, so now let's go back to the case where we have boundary events. So if you consider parameters at the boundary that are greater than 1, so for example, on 1 alpha plus is greater than 1, what happens is that here on the horizontal side, you will have a lot of points generated by the Poisson process. And the path to maximize the number of collected points will stick to to this side. And so basically you don't expect, you expect like a trivial behavior. So then the fluctuation will be under the appropriate scaling will be described by the Gaussian distribution. So basically the interesting regime is the one when alpha plus and minus, the boundary parameters, are in the interval 0, 1. And this was actually characterized. So this is actually the content of the result that was proved in the first paper of the list that Patrik introduced. So basically, they characterize the fluctuation of the length of this path as an interpolating distribution, as a distribution that interpolates between 3 different regimes. So when the alpha plus and minus are less than 1, so basically this is equivalent to considering the model without boundary conditions. And so the fluctuations are GUE, also in this case. When one of the boundary parameters becomes equal to 1, the fluctuations are described. So one of the boundary competes with the bulk. And so now the fluctuations are described by the GOE square, Tracy-Widom distribution. The O stands for orthogonal. So this will describe the fluctuation of the largest eigenvalues of a superposition of two random matrices in the Gaussian orthogonal ensemble. And then actually the really interesting case is when alpha plus and minus are both equal to 1. And here they obtain these new distributions. Still, it has almost 25 years. that can be described in two different ways. So Patrik presented the description in terms of Fredholm determinants, but actually in the original work of Beck-Rains, this was the distribution was expressed in terms of the solution of a nonlinear second-order ordinary differential equation. And so now, actually, to describe the distribution, so the Beck-Rains distribution, and what I will introduce later, which is the equivalent in our space. Well, I have to introduce, let's say, two topics. So one object and one technique, which are strictly related in this context. So, and the first object that I want to discuss are the Painlevé equations. So, I'm not an expert in this domain, so this is the expertise of my collaborator Mattia Capasso. So for me, it's just trying to give like a basic notions of what are the Painlevé equation and what later will be the Riemann-Hilbert problems, to see how they enter this problem. But it's not really my expertise. So okay, the Painlevé equations are a group of nonlinear second-order differential equations that have been discovered in an analytical context, but actually they became quite popular. So why do we actually were interested in these Painlevé equations in the community of integrable systems and integrable probability and in physics in general? Well, because it was noticed that they arise as reductions of the Soliton equation, for example, the KdV equation, which are actually solvable by inverse scattering. So they have very nice properties in the sense that they are completely integrable, and they have solutions that can be expressed in terms of linear integral equations, despite the equation being nonlinear. And actually, well, they arise in many physical contexts. Here we will see how they appear in, for example, in random matrix theory. And actually, so what are they, more precisely? Well, the Painlevé equations, they answer the following questions that was posed by Picard, I guess, in the 70s. So it's a matter of, it was a question of a classification of ODEs. So, and the question was, which second order ordinary differential equation of this form, so the second derivative of u equal to certain function of x, u prime, such that f is rational in u and u prime and analytic in x. Well, which of these equations have the property that the solution have no movable branch points? So this is known as the Painlevé property. So meaning that the location of the multivariate singularities do not depend on the initial condition. And so actually they found a collection of 50 canonical equations that actually, for many reasons, they can be reduced to the interesting cases are actually the 6 canonical Painlevé equations whose solution are known as the Painlevé transcendent. Well, why this name? Because actually, so the Painlevé equations can be thought as a nonlinear analog of classical special functions, but actually their solutions are transcendental in the sense that they you cannot express them in terms of previously known functions. Even if for some cases of you can introduce a parameter in this equation, and for some special cases you can actually have rational or solutions or solution in terms of special functions. So the equation that plays a role in this context is the Painlevé 2. It's actually strictly related to the Tracy-Widom distributions. So the Painlevé 2 equation has this expression. So second derivative of u equals to 2u³ plus xu plus alpha, a complex parameter. And actually you can characterize the solutions for different values of this parameter alpha. So for example, it was proved that for alpha positive integer or half integer, the solution are actually rational or can be expressed in terms of the Airy function. The case that is interesting here and is related to the random matrix theory is the one where alpha equals to 0. So this is known as the Hastings-MacLeod solution, where you add the boundary condition that u of x behaves as minus the Airy function for x going to plus infinity. And actually, so what is the relation between Pauli-Levi-2 and random matrix theory? So now we define these three objects. So V defined a function defined to be such that its derivative is u squared. F is this expectation of 1/2 V of V, and E is the expectation exponential of 1/2 the integral of the solution to the Pauli-Levi-2 equation. So once we have these three objects, well, we can describe the Tracy-Widom formula distributions in the following way in terms of these V, F, and E functions. So we have the GUE, which is F squared. GUE is this product of FE, and the GSE, so the Gaussian symplectic ensemble, can be expressed as this product of FE plus FE minus 1 divided by 2. And actually also the back range distribution as this form in terms of, well, there is this product of F squared E4 times this parenthesis, which is written in terms of solution to the Pauli-Levi-2 equation. And this can be seen somehow as a, so this term between parentheses and E4 can be seen as a sort of a perturbation, finite rank perturbation of the GUE Tracy-Widom distribution. Okay. So actually now we want to understand how this Pauli-Levi-2 solution appear. And to do this, so the Pauli-Levi-2, so the back range distribution appears when you look at the parameters at the boundary alpha plus and minus equal to 1. And so now we want to understand how this U, so this solution to Pauli-Levi-2 appears in the back range distribution. So we have to understand what happens at the transition in when alpha plus and minus go to 1. To do this, actually, we have to introduce another technique. So we introduce another context, which are the Riemann-Hilbert problems. So this is still just to give a sort of a complete context of what are the techniques at the object appearing. So if it is not necessary to really understand what is a Riemann-Hilbert problem from the technical point of view. It's just that it is used, the techniques used by backrange rely strongly on Riemann-Hilbert problems for the Pauli-Levi-2 equations. So what is a Riemann-Hilbert problem? So this is the problem of finding an analytic function in the complex plane having a prescribed jump across a curve. So basically we have, let's say that we have an oriented contour, call it gamma, in the complex plane. So the orientation will define the plus and minus side. And now we have a map, let's call it G, that goes from gamma to the set of n times n integrable, invertible complex matrices. And so the Riemann-Hilbert problem determined by gamma and G consists in finding the an n times n matrix valued function phi, which has the following properties. So the first property is that it's analytic everywhere, but on the curve gamma. Then the limit phi minus from the minus side, to the curve from the minus side, and the limit to the curve gamma from the plus side, called phi plus, are related by this G matrix. So by this relation, this is called the jump property for Z belonging to the curve gamma. And then you need an asymptotic condition. So most of the cases, the asymptotic condition will be that at infinity, phi will approach the identity matrix. So here, we will actually consider one specific Riemann-Hilbert problem, which is the following one. So gamma will be the real line oriented from plus infinity to minus infinity. This is a peculiar choice, I admit, but so this is the choice that this is a convention actually, so it can be defined otherwise in a more natural way, but this is the choice that was made by Beck and Rains in their papers. So I decided to stick to it to avoid the rise of science problem and conventions. So I will stick to this convention. So now we look for this matrix valued function that is analytic in the complex plane minus this real line, and the plus limit and the minus limit are related by this jump matrix. So if you are familiar with the Airy function, so you see that this is already, so the jumps have a very familiar form. And then you have the asymptotic condition that basically at infinity, the solution has to approach the identity. So why do we study this specific problem? Well, because this is related to this is the Riemann-Hilbert problem associated to the Painlevé-2 equation. How do we see that? Well, let's take the solution of this Riemann-Hilbert problem and take the expansion of M around infinity. So you see that the first order term of the expansion is expressed in terms of solution to the Painlevé-2 equation and this V function that was the integral of U square. And so now that we have this, let's see how this will appear in the problem of the polynomial growth model and in the Beck-Rains distribution for the stationary PNG.
Just a quick question.
Yeah.
So this is a simple Taylor expansion that is linked with the V and the U. What you said on the previous slide, that this M1 that has this form is just a Taylor's expansion, or I didn't quite get it.
I'm sorry, I don't. So
how did you get the form of M1?
Oh no, I did not explain it. So it's,
okay.
No, it's
okay.
but you take the expansion of the solution. Yeah, no, I did not explain it. Just that I'm just stating that the first order, so the term of the first order for the expansion of the first order correction. So it can be expressed in terms of V and U. I'm not.
Okay.
Yeah, sorry. So okay, so now let's see what is the how this Riemann-Hilbert problem appears in the PNG context. So let's define these two functions A and B that are written as are given by entries of the solution to the Riemann-Hilbert problem associated to Painlevé-2. And also we want to study the distribution of the PNG model with external sources for different values of alpha plus and minus. But still we want to see what happens around 1, which is the interesting case. So we defined the scaling for alpha plus and minus in the following way. So we have 1 minus 2w plus minus, that will be the parameter that will appear in the limit, divided by cube root of t. So in the limit for t going to infinity, the fluctuation of the length of the height function, or the length of the longest path, or the longest increased subsequence, will be described by this distribution h that will depend on the parameter w plus w minus, and is expressed in the following form. So it is expressed in terms of this A and B function, so the solution to the Riemann-Hilbert problem that we just saw, and f squared. So this will be the GUE Tracy-Widom distribution. And actually, if you study the behavior of H according to the values of W plus and W minus, you see that H interpolates between the three distributions that we saw before. So when you take W plus and minus goes to infinity, which will correspond to the case boundary parameters less than 1, you will see the GUE Tracy-Widom. When when W plus or minus is 0, corresponding to alpha plus or minus equal to 1, you will have GOV squared fluctuations. And the case W plus minus equal to 0, basically alpha plus minus equal to 1, well, you will observe the back range distribution. So you have asymptotics for this A, B, and V that will give you this formulation, this formula. Okay. Okay, so now let's go back to the PNG in our space. I guess I sped up a bit. I can relax. So this is so let's explain what is the setting in our space. So this is very similar to what Patrik presented in his talk. So we have now a Poisson process in this triangle with parameters with intensity t square. We add the Poisson distributed points on the horizontal side of parameter alpha plus t, and now instead of having Poisson points on the vertical side, we add the Poisson points on the diagonal of parameters alpha minus t. This can be seen equivalent as a PNG mod where
are the alpha plus and alpha minus times t, or this alpha plus?
No, it's alpha plus and minus are the parameters, and then it's multiplied by t. Yes, exactly. So this is equivalent to, you can see this as a symmetrized version of the full space PNG, basically where you generate points in the unit square and then you symmetrize the point with respect to the diagonal. So this is an equivalent interpretation. And then you also look for the quantity of interest. It is always the length of the path that collects the highest number of points. So let's say that we get rid of the Poisson process on the horizontal side. So we put alpha plus equal to 0. So now the fluctuation of L, of the length, have been characterized by back range in the first of the 3 papers that I mentioned. And actually you see that, so first of all, the problem was studied in a different setting. So in this paper, actually, Beck and Rains, they analyzed the problem of the longest secreted subsequence in random permutations with different symmetries. And this was one of the cases that they analyzed. And so the PNG model in half space will correspond, so this L for the PNG in half space will correspond in this setting to the length of the longest increased subsequence in a random involution. So basically a permutation where you have fixed points. And so the way of associating the involution to the so the path to the involution is the same. So you take the y coordinates of the points visited by the path related to the x coordinates. So and this is the the longest increased subsequence obtained, for example, from this path. And now here the fluctuations actually we expect the behavior to depend on the boundary parameters. Because, well, what happens if you here the transition is given by the value of the value at the bound on the diagonal being equal to 1. So in this case, what you observe that the fluctuation of L are described by the GOV Tracy-Widom distribution. When alpha minus is less than 1, the fluctuation will be GSC Tracy-Widom. And when alpha minus is greater than 1, well, here you don't observe anything. Basically, you have to change the scaling. You have to take the square root of t scaling instead of cube root of t, because basically you will observe Gaussian fluctuations in this regime. Well, why? Because basically we have the same problem of we are in the same situation as in the full space. If the values if the parameter of the Poisson process on the diagonal is greater than 1, now there will be a lot of points on the diagonal, and the path will tend to stick to it. So you will the bulk will not play a relevant role to perturb the it stay on the diagonal. Okay, so now let's put back the horizontal, so the Poisson process on the horizontal side. So now we are back to the case where you have a nucleations event on the diagonal and on the horizontal side. So so this is the result that I wanted to present. So basically, what we did with Mattia Cafasso, Daniel Hoffner, and Harriet Walsh was to extend the work of Beck Rains using similar techniques. So generalizing them to the full space, to the half space case, to characterize the whole regime of the fluctuation of L. And so what we obtained was that, well, as expected, when the parameters at the boundary alpha plus and alpha minus are strictly less than 1, well, we are still in let's say, the classical half space case. So it's like the horizontal Poisson process doesn't play any role in the scenario. And so we have GSE fluctuations. When one of the parameters, alpha plus or alpha minus, is equal than 1, and the other is strictly less than 1, now we have GOE fluctuations. And the interesting case, or the novelty, is the case when alpha plus and alpha minus is equal to 1. And here we characterize like this Beck range distribution in half space. Actually, just a remark, so this half space Beck range distribution was observed also for by Barakan, Klagenbrinkel, and Dussal for the half-line KPZ equation with a stationary initial condition. So basically, when you start from so when you have the KPZ equation in half line with a reservoir with Neumann boundary condition, and starting from a Brownian configuration. So basically, what they obtained this new distribution in terms of a Fredholm determinant, and then they derived the same expression that we got, but in a, let's say, in an informal way. So in this case, we actually formalize the proof and somehow prove the conjecture for this Beck range distribution in half space. Okay, so, well, what is the advantage? So why, so before describing the distribution, let me show you a couple of plots, and then, so here this is, so the advantage of the formula that I will introduce, that I will present later, is that, well, it is very easy to do numerical simulations. And so we were able, for example, to attain the plot of and some estimates on the average and the moments of this half space Beck range distribution. And so here we compare the probability density function and the cumulative distribution function for the Beck range in full space in blue and half space in orange. So it can be shown, for example, that the average is 0 in both cases, and you can find also expression for the tails. So here, for example, the right tail will decay as exponential of minus 2/3 of x to the power 3/2. And the left tail will be e to the minus x cubed divided by 24. So these are decays that are let's say, large deviation functions that are consistent with what had been found for the full space backrange distributions. And here, so we compare the different Tracy Widom distributions, so the cumulative for the different Tracy Widom distributions, just to give the full picture. And here, what is interesting to observe is that, well, there is this sort of a interpolating behavior that can be observed here in looking at the cumulative of the GOE square, and backrange. So if you remember, in the full space, we had this, according to the values of alpha, plus and minus, we had this transition between GOE square, and backrange. And here in our space, you have a similar behavior. So the transition was GSC, GOE, half space, backrange. And here somehow you can, let's say, read it when you plot the cumulative distribution functions. Okay, so now let's go to the main result. So this is the formula for the backrange distribution in half space. So here you can see you have a formula which is analogous to the backrange in full space. The difference is here you have, instead of having V, you have V of x minus U of x divided by 2. And here, instead of having E fourth is F squared, you have E cube F. But the structure is very similar. And so this is one way of representing the backrange distribution. So this is very convenient. So in this context, this is a very convenient form because it is very easy, once you have this expression in terms of Painlevé-2, well, to estimate the moments, to make this kind of plot, for example, and to obtain the tails, because basically the asymptotics for the Painlevé-2 equations are well known. So once you have this expression, it's almost immediate to obtain all sort of estimate and asymptotics and large deviation principle that you might need.
Alessandra, just short question. This
Yes.
F and the E were the one for
The same
most
yes. So the exponential of 1/2 the integral of V, and the exponential of 1/2 integral of U. Yeah. Another is also this different expression. So this is more similar to what Patrik introduced, Patrik presented. So we can compare in full space and in half space. So here you have the structure in terms of a derivative of this product of, so in full space you have GOE Tracy Widom times this integral of e to the fourth. That should correspond somehow to the perturbation term that appears also in the determinantal formula. And here in our space, you have the derivative of, so you have the same object, but here you have this ratio of GOE and GOE Tracy Widom. And this expression can actually be derived directly from the formula in terms of Painlevé-2. But still, you see the same structure that Patrik explained. So and now let's give briefly the sketch of the proof. The strategy is similar, so the idea, the setting is very similar, but the techniques are completely different with respect to what Patrik explained in his talk. So the starting point is always the same. So we start from an integrable model. So we start from we modify slightly the setting. And in this case, where we take the same LPP, Poisson LPP with boundary conditions, but we add in the origin a geometric random variables of parameter alpha plus times alpha minus. The fact that you have a geometric random variable here might sound weird, but so the point is that this Poisson limit, as Patrik explained, is the limit of a geometric LPP. And actually here, when you take the limit to Poisson, well, this geometric random variable here is not affected by the limit. So you stay with when you take the Poisson limit, the point, so the random variables in the back will generate these Poisson points, but the random variable here in the origin will stay the same, will not be affected. Okay, so we take these models, and we observe that basically the model that you're interested in can be simply obtained by deconvoluting this L plus, so this model, and the geometric random variables. And actually, I mean, we want to do this also because in the regime that you're interested in, well, the geometric random variables has infinite means, so it will give like a singular term. So going back to the integrable model, so we start from this model because it was proved by Beck-Rains in the context of longest increased subsequences. Well, it was proved in the context of a geometric LPP, actually, that by a series of RSK correspondence and sure function identities, you can express the distribution of the last passage time for this model, so for L plus, as an expectation, so in terms of moments of the trace of a random variable in a specific compact Lie group. So in this case, it would be, since we're considering a symmetrized model, it would be the moments of the trace of a random element in the orthogonal group. And actually, this can be reformulated as an expectation over the orthogonal group of this determinant. So here you have so the distribution of L plus T can be expressed of, okay, there is this prefactor that comes from the geometric to Poisson limit from the partition function, and this expectation over the orthogonal group of the determinant of, so here you have e to the t of u, right? Actually, I mean, you can, if you take the determinant, you can see that this would be simply e to the t trace of u, and then this perturbated by this determinant of 1 plus alpha u, 1 plus alpha minus u. There will be a sort of a perturbation given by the presence of the boundary processes. And now, to go back to the original, so to the model that we want to study, you have to deconvolute the random variable, the geometric random variable, and this is the effect that the convolution produces to the distribution. So the prefactor will be the same, and now you, instead of having only this expectation over the orthogonal group for a matrix of size L, so that we call TL, you have a difference of TL minus alpha plus times alpha minus TL minus 1, which somehow gives the vibe of a derivative. So somehow you see that the same structures appear in different contexts, but with the different techniques that we used. And so just a small remark. So this is like somehow a very compact way of expressing the distribution of L. But actually, you have to be very careful when you study the symmetrized model, which is much harder than the case on the non-symmetrized or the full space, where everything will be on the unitary group. Because now you have to consider that everything has to be done over you have to take the average of this expectation over the connected components of the orthogonal group. So you have to consider the component where the determinant of the element is +1 or -1. And actually, this is not the only subtlety, because the result, the outcome will depend also on the parity of L. So we have slightly different formulas if L is even or odd. But this I will I just mentioned that this is a technical subtlety, but it will be clear later why this happens. So basically, now we want to understand what happens. What are these TL objects? So the idea is that we want to express this expectation over the orthogonal group as simple objects, and then you want to do the asymptotics analysis by the scaling L with the typical scaling. So L would be 2 times t plus x prefactor t to the cube root of t. Well, the first step will be to rewrite more explicitly this expectation. So here, for example, I chose a particular k. So I chose to look at the component with determinant +1 for even L. So this is O plus of 2L. This is the notation that the convention that was chosen. And here, basically, by Weyl integration formula, you can rewrite these expectations for the determinant of a function of u as this multi-integral, where h is evaluated on the eigenvalues of u times this van der Monde. And now you see, for example, why the parity of L plays a role. Because here, well, if L is even or odd, well, here H might be, well, the eigenvalues are complex conjugate, but you might have eigenvalue plus or minus 1 according to the size of the matrix. And in one case, you might have only +1, only -1 according to the size of the matrix and the value of its determinant. So this is why you have to distinguish these 4 cases. So L odd even and determinant +1 or -1. Then, well, you will write, we will write this van der Monde in terms of 2 sets of monic orthogonal polynomials. This is an explicit identity that, and then by under-AF identities, we can express this multi-integral as a determinant of a matrix where on each in each entry you have this single integral of h evaluated on e to the I theta h e to the minus I theta times this product of orthogonal polynomials of different degrees. And now, well, now this is the expression of TL. So was the case that we wanted to study. So the idea is that we want to get rid of this determinant of the factor 1 plus alpha plus u, 1 plus alpha minus u from the expectation. So that in the end, we have like a prefactor that will depend on alpha plus and alpha minus. So everything that is on the boundary times the expectation of e to the 3 trace of u. So the determinant of e to the 3 of u. Which will be much simpler to study. And to do this, well, there are two results that are used to obtain this formula. One is Christoffel formula that allows us actually to write this integral basically to put the contribution of the orthogonal polynomials in this integral outside of the integral by changing the hard measure of on the group. And then you have to use a Szego transformation because, well, Christoffel formula is available for a specific set of orthogonal polynomials. And then you want to express everything in terms of these pi, of these pi's, which are the orthogonal polynomials on the unit circle, which are basically monic orthogonal polynomials that have this orthogonality relation with respect to this measure, e to the t z plus z minus 1, this z divided by 2 pi I z. And so now you have basically this expectation of e to the t trace of u, which will be much simpler to study. And now you have this huge factor in terms of orthogonal polynomials on the unit circle and their conjugate. So this pi star are simply z to the L, pi L of 1 over z. And here you have this pre-factor 1 minus alpha plus alpha minus times alpha plus alpha minus that actually are represent singularities for this term. So let's see what we have to do next. So now we have this expression again. So now you see that you have these two singularities, one in alpha plus times alpha minus equal 1, and one in alpha plus equals alpha minus. Well, and this is actually annoying because the case we want to study is when alpha plus equals alpha minus equal 1. And there is a way to deal with the singularity. So for the second singularity, so alpha plus minus alpha minus, actually it is possible to use a recurrence relation for orthogonal polynomials on the unit circle of higher degree in terms of orthogonal polynomials of lower degrees. And actually you can algebraically get rid of this singularity. But then you're still left with the singularity alpha plus alpha minus equal 1. So now we have reformulated everything in terms of orthogonal polynomials of the same degree. This is necessary because we want to perform asymptotic analysis in L. And actually, if you have different degrees, there will be, if the orthogonal polynomials are expressed in terms of different degrees, there will be some non-trivial oscillatory factors that will appear in the asymptotics of these objects. So it is a useful step to put everything in terms of all this pi L in terms of the same degree. And now, so this object is pretty easy to estimate because, well, either you can see it as it's possible to see it as a Toeplitz plus Henkel determinant, for which there are many asymptotic results, or you can express it just to stay in the same setting as product of norms of these orthogonal polynomials pi's. And now basically the last step to do is to get rid of to treat this singularity. Sorry, here it should be equal to 0. I made a mistake. And this is done by applying L'Hopital rule. So basically here you would have derivatives of pi's that you can express in terms of again order orthogonal polynomials. You have to manipulate the expression, but then you get rid of the singularity. And then what is left is just to perform the asymptotic analysis for the pi L and the norms of these orthogonal polynomials. And this is obtained by constructing a Riemann-Hilbert problem associated to these orthogonal polynomials on the unit circle. And so when you look at the asymptotics of these of the pi's, you obtain the entries of the Riemann-Hilbert problem associated to the Pain-Levé-2 equation that we saw in the full space case. So you obtain the same function A and B. And basically this is the last step, and this is how you obtain and then you perform the asymptotics of B and A for particular values for W plus and minus equal to 0. And you obtain the final expression of the half space back range distribution. And so now basically what we saw a few results for the stationary LPP in half space, and now we wonder if these results are somehow related. So, I mean, we should expect that this distribution is universal for a stationary model, for a symmetrized model in the KBZ universality class, starting from stationary initial conditions. So, for example, one interesting question would be if it is possible to relate this Pain-Levé formula for the distribution to the Fedon-Pfaffian formula that we obtained with Patrik and Dan. There is a connection that was actually used by Barakan, Kazimir Dussal to a Fredholm determinant formula, but still there is a gap missing with the Fredholm-Pfaffian expression. And then actually would be, so we obtained the distribution for stationary distribution for PNG, for exponential LPP, for half-line stationary KPZ equation. It would be interesting to see if also using similar techniques, so we can obtain the same expression for example, the discrete time TASEP. This could be done with the same techniques, but probably a different set of orthogonal polynomials will appear. And so there will be different asymptotics to consider. And then a question that could, like an extension of this work, could be to see if the same technique, so using Riemann-Hilbert problems and asymptotics of the Pain-Levé-2, could be used to extend to obtain different results for other stationary initial conditions. So the stationary initial condition that Patrik was mentioning at the end of his talk after Dominic's question. So there is this half space. So there is a different family of stationary initial condition that was obtained by Barakan, Kazimir Dussal for the half space log gamma polymer. And there is also the possibility of rewriting them in a geometrical PP setting. And it would be interesting to see if actually these techniques could be extended also to that case. And that's it.
Yeah, thank you very much. So yeah, we have again time for questions. So again, feel free to unmute yourself. Or if not, let me maybe start with one. Get it started. So everything you described is like for point to point, like somehow point to point. Like you go from 0, 0 to 1, 1, right?
Yeah.
Can you say anything about, let's say, point to line, or let's say even like 1 point slightly off the diagonal, like 0, 0 to 1 plus epsilon, 1 minus epsilon?
Okay, so off the diagonal, in this setting, no, because actually, so this sort of Poisson LPP is strictly related to this problem of longer secreted subsequence in random permutation. So to look at something outside of the diagonal, you have to go to the discrete setting, so either geometric or exponential LPP. I don't think that there is a way of keeping the Poisson structure by going off diagonal. For the point to line, this should be related to. So I mentioned these works by Beck-Rains, where they studied the problem of long executed subsequence in random permutation with various symmetries. This is one of the 5 cases that they look at. So they look at well, non-symmetrized, so basically full space. So random permutation. They look at the 2 diagonals, and they look also at the symmetrization. So main diagonal, the other diagonal, and also reflection with respect to both diagonals. So, and the point to line should correspond to this case, I guess. So, there is, so it is true that one could add to this case another boundary condition on the horizontal, but I don't know how things would work actually, because it would be kind of a weird setting to have because you would have Poisson points basically on each side, and I'm not sure this might give us something particularly interesting. But in case if you want to look at the at the case where you don't have the points on the horizontal line. This is in this Beck-Rains paper, and there is always like a interpolating behavior for the depending on the number of fixed points in the involution between GSC, GOE. I don't remember exactly what is the asymptotics in this case, but this is like there is an analogous behavior depending on alpha, let's say, where alpha is the number of fixed points, say, in the involution.
Yeah, thanks.
Maybe
More
a remark.
questions? Yeah.
Indeed, what is a bit strange in this setting, now in the LPP setting, is that, say, for point-to line, so for generic initial condition, for TASEV, there was this orthogonal strategy, and it was used to get to, say, to the KPZ fixed point. But the natural point-to line, it does not correspond then to a positive measure in this setting. So for the first result, indeed, were all obtained by the LPP, but for, say, the limit process, like the ERI1 process for point-to line, was more in terms of particle system directly. It's strange that in some sense they are tightly related, but there is not the analog written down for the LPP feature directly. In principle, there should be something, but nobody ever really wrote it down, probably. There was a question for Alessandra. In terms of asymptotic analysis, were there any? So there was the derivation of the formula, but then the asymptotic analysis for the Riemann-Hilbert was similar to the full space, or there was needed some new ingredient?
No, the asymptotics analysis. Okay, so for the Riemann-Hilbert is the same, because basically the objects are appearing are the same in full and half space. So basically, they get asymptotics for Painlevé-2 via the Riemann-Hilbert problem, and then they construct this other Riemann-Hilbert problem for the orthogonal polynomial to the unit circle, and they get the asymptotics for these for these objects. It's just a matter of how you rewrite the different expectations for each symmetry.
But in some sense, could you just use the old asymptotic by Krenz, or you needed to do something more refined?
So the asymptotic cells that we use are exactly the ones that can be found in the Beck-Rains paper, asymptotics of monotone
Evolution.
The difficult part is actually in manipulating the expression that you get for the symmetrized case to get, to get the appropriate terms, so the relevant terms.
Okay, it's clear.
Yeah, but yeah, no, the asymptotic analysis is already done, so you don't really need to. The Riemann-Hilbert problem is already solved. That's why I could manage
Good for you.
to go to that paper because the results.
Yeah, good. Any more questions, remarks, comments? So doesn't seem to be the case. So let's thank both speakers again. Very nice talks.
Thank you.
Yeah, thanks. Okay, and yeah, we continue in the new year. I think January 13th is the next one.
Okay, thank you very much.
Well, thank you for giving the nice talks. Yeah.
Pleasant holidays. Good transition into the new year.
Yeah. Happy holidays indeed.
Nice
Hi, Martin.
transition.
Hi, Martin.
Bye-bye.
Bye.
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 Yeah. Patrik, you have maybe like super briefly. So you saw the WhatsApp, so just
Yes.
yeah, let me know if there's anything. I'll implement the comments from section 4, I
I
guess today.
continue from where the point I was, and then step by step.
Okay. Perfect. Yeah. Cool.
Bye-bye.
Okay, that's I think all the like
Yeah.
math related
Don't forget to
things.
send us your slides so
I
that
will
we
send
can
them. Yeah, I have an appointment now, but I will send them later this evening. Don't worry.
Okay.
Perfect.
Bye
Thank
bye.
you.
That's good. Yeah.
Bye.
Have a good time. Ja. Ja. Gibt's für uns irgendwas noch aktuell? Oh, bitte, ich kann dich gerade nicht hören. Irgendwas stimmt nicht. Ja.
So.
Jetzt.
Hören Sie mich?
Ja, jetzt geht's.
Nee, ich wollte nur Leute rauswerfen.
Ja.
Ja, okay. Ich habe wieder gecheckt. Ich habe immer noch nicht deine Zustimmung, aber du weißt, wir
Okay.
treffen uns dann am 10.
Genau. Ja, das ist, also wie gesagt, ich finde es ziemlich komisch, weil ich habe drauf
Ah,
geklickt und
nee,
bei mir steht es im
komisch. Hier
Kalender drin.
auf meinem Laptop sehe ich einen Tick, aber auf meinem
Aha.
iPad, ich glaube nicht.
Okay, komisch. Ja, nee,
Aber okay,
aber
du hast es gesehen. Punkt ist, du weißt, klappt auch zeitlich.
ja, passt. Alles bestens.
Ja, ich habe einfach ich habe genommen, ich glaube, 9 Uhr morgens für euch als Startpunkt.
Ich glaube 10 Uhr für uns, aber
Also sogar 10, okay. Aber ich wollte in jedem
ja,
Fall
ist
es so
besser.
machen. Nee, ich meine, ja, für die Angebote habe ich einfach 9, ich glaube, bis 1 oder so eure Zeit oder bis 2 eure Zeit gewählt.
Mhm. Ja, genau. Ja,
Und
das ist
das ist
perfekt.
dann für mich, ich glaube,
So
2
5
bis
Stunden.
5 oder 1 bis 5 und für Luisa dann 2 bis 6. Und ich habe gehofft, eine von
Genau.
diesen soll für uns alle klappen.
Ja, passt.
Äh, und dann, okay, und das machen wir dann direkt, bevor wir unsere letzte 2 Seminare haben.
Genau. Also ich habe Volker und Ben schon angeschrieben, dass
Mhm.
sie mir quasi Title Abstract schicken. Wie gesagt, sobald sie das machen,
Mhm.
habe ich das dann.
Vielleicht,
Kann's online
was
stellen.
wir machen könnten, ist schon im Voraus eine E-Mail an Luisa und Roger zu schicken und den beiden vorzuschlagen, dass sie sich vielleicht überlegen sollen, wen einzuladen. Weißt du, weil
Okay.
wir hatten wegen Sommer hatten wir einfach 2 Monate Zeit, bevor wir
Mhm.
angefangen haben.
Ja,
Bei denen wird das deutlich knapper,
das stimmt.
weil ich nehme
Ja.
an, die werden anfangen, vermutlich was Ende Februar.
Ja, nee, dann ist ein sehr guter Punkt. Also Roger sehe ich natürlich jetzt gleich dann noch beim Mittagessen, dem kann ich es
Was
gleich
Sinn
sagen,
machen würde,
aber
vielleicht
ja.
ist einfach mit denen schon diese Doc-Datei oder was für ein
Mhm.
Format die ist auf Google Drive,
Mhm.
mit denen schon zu teilen.
Ja.
Äh, und sagen, okay, die technischen Sachen
Mhm.
können wir in jedem Fall 1. Januar diskutieren, aber vielleicht
Mhm.
sollten die sich einfach die Liste von bisherigen
Ja.
äh, Sprecher anschauen
Mhm.
und sich überlegen, entweder zusammen oder getrennt,
Ja.
welche Paare soll ich die E-Mail schicken oder?
Gerne.
Okay.
Ähm, ja. Genau, weil dann kannst du es, glaube ich, gleich freigeben, das Dokument. Und das ist, glaube ich. Oder
Ja.
du würdest es einfach anhängen. Oder
Ich
freigeben ist
glaube,
wahrscheinlich besser.
wenn ich glaube, wir können es einfach mit dem expliziten Link teilen, weil da steht kein Geheimnis drinnen, oder?
Nee, das Ding.
Ich glaube, die
Ich
einzige
meine nur, dass
Sache,
es technisch geht.
die theoretisch vielleicht nicht zu verteilen wäre, ist, dass Bernoulli Society, was die uns gesagt haben im Sinne von die Domain-Verlängerung.
Ach so, ja, aber Das müssen sie ja eh wissen. Also das kommt ja.
Ja, nee, aber ich meine, weißt du,
Aber,
dass jemand Externes das nicht
ach
sehen
so,
soll.
ja, ja. Ach so, ja, ja, klar, klar.
Aber
Nee,
ansonsten, ich
aber das
glaube,
ist mit dem Link, denke ich mal, überhaupt kein
ja,
Problem.
ja, okay. Dann ich schreibe das in den nächsten paar Tagen
Mhm.
per E-Mail.
Nee, super, danke. Dann, genau, aber
Hm.
ich kann, also Roger, wie gesagt, kann ich gleich schon mal vorwarnen.
Ja, du
Und
kannst,
dann,
wenn er schon irgendwelche Ideen hat. So diese
hm?
Gruppe, so Alessandra und wieso bin ich so?
Patrick, ja,
Hm?
Patrick, oder,
Patrick, ja, siehst du, ich habe
ja,
Ferrari.
ja, ja,
Ferrari kam hier vorne.
alles gut.
Du kennst ihn direkt, oder?
Wen meinst du jetzt? Äh,
Patrick.
Patrick. Ich war ja sein Postdoc für 2 Jahre.
Okay, so, aber wieso haben wir den beiden als Paar? Weil du kennst Alessandra auch von deiner Postdoc-Zeit, oder?
Achso, ne, Alessandra kenne ich von verschiedenen Konferenzen. Wir haben auch was
Okay,
gemeinsam organisiert in Oberwolfach.
okay.
Und sie ist ja ehemalige Doktorandin von Patrick.
Aha, okay.
Also die beiden haben quasi zusammen, also gerade diese Half-Space-Sachen sind jetzt so
Mhm.
3 Jahre ungefähr her und sie hat halt dann quasi jetzt ein bisschen in die andere Richtung weitergemacht mit,
Mhm.
also mehr die analytische
Ja, ja,
Seite.
nee, weil ich kenne Alessandra total getrennt von Bonn und so, deswegen ich
Achso,
wusste,
okay.
dass du mit ihr auch sozusagen eine direkte Beziehung hast.
Genau, also wie gesagt, also sie hat bei Patrick ja promoviert und war dann in Lissabon und jetzt dann in Angers.
Jo, jo, jo.
Also deswegen, also das war, glaube ich, so ein bisschen die Idee, warum die beiden.
Mhm.
Und weil sie eben beide
Patrick, ist der Italiener oder?
Schweizer, aber italienischsprachig. Der kommt
Mensch,
genau
wie
aus dem
viele
Grenzgebiet.
Schweizer es gibt, die einfach, ich war auch total, ich bin immer noch verwirrt, dass
Mhm.
Daniel Ulci, okay, der ist Schweizer offensichtlich
Ja.
wegen seinem Nachname, aber
Mhm.
ich dachte, der war von der deutschen Seite, aber nee.
Okay,
Nee,
wirklich?
der ist aus Lausanne, Französisch sprechend.
Okay, krass.
Also ich hätte nie erraten.
Ja, nee, nee, echt nicht. Nee. Ähm, ja, krass.
Und
Ja,
natürlich
auf jeden
auch
Fall.
Haira, wieder
Ja, ja, klar.
Schweizer.
Ja. Ja.
Äh,
Nee, es gibt viele, viele Schweizer. Also das ist schon, das ist erstaunlich.
ja. Aber
Ja, aber
Moment, Gilles Coupon, der ist Franzose, oder?
der ist Franzose, kommt aber auch aus der Gegend. Also jetzt nicht, der ist nicht Schweizer, aber er kommt quasi aus dem Grenzgebiet. Aber zum Beispiel Tassian ist, weiß ich gar nicht, ob er nicht sogar beide Staatsangehörigkeiten hat.
Mhm.
Also der kommt aus dem Bergdorf. Und also, aber alles so die Gegend
Da
da.
muss es irgendwas im Wasser geben.
Nee, ja, also irgendwie das Alpenwasser ist gut. Also, was da frisch
Ähm,
abgezapft ist. Nee, nee, Patrick ist ja auch in den Bergen aufgewachsen. Also, ich,
vielleicht, okay, so
ich weiß nicht, ob du
Alpenwasser
mit,
und frische Luft.
ja, ja, nur als Vorwarnung, wenn du mit ihm mal wandern gehst. Er ist schnell. Er ist sehr
Ja.
schnell.
Ja, wenn ich
Und auch,
jung war oder wenn ich Kind war, habe ich mit meinem Vater auch oft
hm,
gewandert in
ja,
Alpen und so, aber schon
hm,
lange her.
naja. Nee, der hat ein Tempo drauf. Also auch bei Oberwolfach so mit Abstand quasi am schnellsten und er war schon langsam unterwegs. Also, nee, nee, der ist eine Maschine. Und da hast du schon manche, die da wirklich, ja, wenn du da aus der Gegend
Ich
kommst,
muss
dann.
sagen, Oberwolfach, ich weiß nicht, ich habe bisher immer einfach Pech gehabt mit Wetter.
Okay.
War immer
Ja,
super nass und dreckig.
ah.
Also
Ja,
ich
die
weiß
Konferenzen im
nicht,
Sommer sind schöner da. Also
ja,
das
ich
ist,
war einmal im Winter und einmal im Frühling.
ja,
War einfach
dann,
Okay, im Winter war schön zu sehen
ja.
zumindest.
Mhm.
Aber ansonsten, wie gesagt, man könnte nichts draußen tun.
Ja. Auf der anderen Seite sei in der Hinsicht froh, du hast die Zeckenzeit vermieden.
Ich habe Zecken, es gibt Zecken da.
Oh ja, nicht gerade wenige, das ist Zecken-Hochrisikogebiet.
Ah, ich dachte, dass das hinreichend kalt ist, keine Zecken zu haben.
Nee, 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 es ist wirklich Hotspot in Deutschland für Zecken.
Aber ich dachte,
Oberwolfach.
Zecken brauchen irgendwie Mittelmeerklima oder so.
Nee, 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 nee. Also Oberwolfach ist wirklich, im Sommer ist es mit Zecken relativ gefährlich. Also das ist so der Vorteil, im Winter hast du das Problem halt nicht. Aber gerade im Sommer ist es ziemlich gefährlich.
Moment, das ist komisch, weil zum Beispiel, okay, ich weiß nicht, ob sich das in den letzten 10 Jahren geändert hat, aber zum Beispiel in Slowenien hatten wir immer
Mhm.
Zecken am See, sorry, am
Mhm.
Meer,
Ja.
aber zum Beispiel im Nordslowenien, was ist immer noch deutlich südlicher als
Mhm.
Deutschland, gab es keine Zecken.
Nee, in dem Fall, nee. Also die Wälder sind wirklich Zeckenhochgebiet in Oberwolfach.
Aber das sind nicht diese Tigria-Zecken oder wie heißen die?
Nee, aber die sind trotzdem gefährlich. Also die meisten haben schon so Borreliose, FSME.
Oh,
Ja,
wow.
ja, also Oberwolf, also wie gesagt, deswegen musst du nicht, also es hat auch Vorteile, wenn man nicht im Sommer hingeht.
Okay.
Also das ist nicht ganz ohne. Also man sollte wirklich auch die Impfung haben, also die FSME. Vor allem halt, wenn du halt durch den Wald wirklich gehst.
Mhm.
Weil so passiert natürlich nichts, aber wenn du irgendwie im
Moment,
Gras
Zecken
da,
normalerweise brauchen Wasser, oder?
ja, ja, aber da gibt's genug.
Okay.
Also wie gesagt, Oberwolfach, Schwarzwald, es ist wirklich Zeckenhochrisikogebiet.
Interessant. Ich habe immer gedacht, dass ungefähr Österreich oder so einfach die starke Grenze
Es
ist.
ist so weit südlich. Es ist schon wirklich, also Schwarzwald ist schon ziemlich südlich.
Ja, aber wie gesagt, deswegen sage ich Österreich, was, weißt du,
Ja, ja, nee, nee,
in
aber
Slowenien nah an der Grenze gibt es keine Zecken.
ja,
Und ich dachte einfach, wenn du weiter nach Norden gehst, bleibt
nee,
so.
nee,
Ja, interessant.
nee, nee. Also wie gesagt,
Weiter
Bayern und
die E-Mail von
Baden-Württemberg.
Patrick an die Gmail-Adresse. Du musst es nicht
Bitte?
tun. Ich leite die E-Mail von Patrick direkt nach
Ah,
die
perfekt.
One World, weil ich werde dann
Mhm.
davon
Ja.
es speichern und so.
Hm. Ah, perfekt.
Ich mache das in den
Ja.
nächsten paar Tagen, weil
Ah,
YouTube
super.
ist unglaublich langsam, bevor man irgendwelche Änderungen an der Metadateien machen kann. Ich verstehe nicht, wie alle diese YouTube-Creators das schaffen.
Also vorproduzieren. Die produzieren halt alles vor, wirklich.
Nee, das ist mir klar, aber weißt du, zum Beispiel, du kannst nicht, ja, okay, wenn du alles zur Sekunde präzis im Voraus weißt, kannst du das auch sofort schreiben, okay.
Mhm.
Weil ja, irgendwelche Änderungen am Server zu machen, ist einfach,
Nee, nee. Die machen das alles schon davor und
ja, ja, und okay, und dann haben die genau Zeitpunkte und so, und das können die dann
ja,
sofort schon
ja.
schreiben. Ja, klar. Weißt du, weil ich muss immer am
Und
Anfang ein bisschen abschneiden.
ja, ja, das ist nervig. Das ist. Wobei heute zumindest am Anfang, glaube ich, müsste man nichts rausschneiden, nur in der Mitte.
Ja, diesmal haben wir haben endlich gelernt.
Ja,
Äh, Ja, das hat alles
nee, passt.
geklappt. Ich
Ja,
muss aber
sehr gut.
sagen, ich könnte kaum folgen, die Techniken, weil das ist so weit aus meiner Welt.
Aber du meinst vom Vortrag?
Ja.
Ja, ja, nee, nee, das ist immer ein bisschen schwer zu sagen, quasi. Du kannst auch Last Passage Percolation sehr, sehr langsam einführen. Aber
Mhm.
Patrick war so, hier ist das Ding und dann let's
Ja,
go.
nee, nee, die wollten
Aber
auch über spannende Sachen reden.
ja, ja, klar. Nee, nee, aber absolut, das ist halt wirklich ein ganz generelles Problem. Also, also wie gesagt, für mich war das so, ja, passt. Also nehme ich mit
Ja, ja, aber du kennst
und hab
das.
trotzdem. Genau, wobei zum Beispiel den analytischen Teil, was Alessandra vorgetragen hat, den fand ich richtig interessant, weil habe ich bisher auch noch nicht so in der Form gesehen,
Nee, nee, ich fand es
dass sie das.
interessant, aber weißt du, ich könnte nur konzeptionell irgendwie folgen, was
Ah,
passiert, aber
nee, aber nee, nee, das Problem ist, allein schon mal, was diese ganzen Threshold Determinants sind. Das ist einfach, das dauert. Und da kannst du nicht, also du müsstest irgendwie über Punktprozesse reden. Dann kannst du da
hm.
vielleicht anfangen, quasi, wo kommen die Dinger her, das Ganze zu machen. Und Patrick hat auch
Ich,
schöne
ich,
Lecture
ich
Notes.
wollte, ich wollte ganz am Ende dann fragen, aber gab es andere Fragen, deswegen habe ich es
Hm.
nicht. Vielleicht weißt du.
Mhm.
So, könnte man, wenn man zu dieser Poisson-Variante geht,
Ja.
könnte man statt Anzahl von Punkten die Länge von Verbindungen zählen?
Ja, kann man.
Und
Da
kommt
gibt
man
es
immer noch
auch.
etwas in die KPC Universality Class oder bekommt man
Äh,
ganz was anderes?
Nicht mehr, wenn du das machst. Da muss man leicht andere Modelle nehmen. Das läuft oftmals unter Brownian Lost Passage Percolation.
Mhm.
Da kannst du quasi sagen, du hast quasi Brownian Motions und du folgst quasi den einzelnen Kurven und optimierst quasi über, dass man quasi springt zu einer anderen Kurve und da bezahlst du quasi immer den Sprung. Und du musst
Mhm.
quasi von einem Punkt zum anderen und darfst halt quasi diese Kurven sozusagen als deine Autobahn verwenden und dann kannst du irgendwann mal zu einer anderen Kurve springen
Aha,
und
und du
kannst
sagst,
theoretisch
dass
wieder.
diese Variante, wo du immer noch die Punkte hättest, aber würdest du sozusagen bezahlen, die Länge der Kanten würde in die Klasse irgendwie landen.
Genau, da musst du halt das Modell ändern. Also zumindest jetzt direkt, wenn du quasi nicht mehr Punkte zählst für Poissonian LPP, dann ist das nicht mehr integrable, also dann weißt du gar nichts mehr. Ich würde vermuten, es ist trotzdem noch universell in KPZ, aber man kriegt es nicht hin. Aber es gibt Modelle, also dieses Brownian Last Passage Percolation zum Beispiel, da macht man das, dass du quasi die Länge zählst. Also und die Längen
Ja,
aufsummierst und darüber optimierst.
ich hab nur mit Prozessen, die eher First Passage Percolation oder Contact
Ja.
Process sind.
Nee,
Ich
nee,
habe von dieser
da ist
anderen
es.
Richtung nie was gemacht.
Ja, es ist ein bisschen schade, weil das Problem ist, diese Sachen da hängen davon ab, dass du wirklich exakte Formeln hast. Und das ist hochgradig speziell. Also da darfst du nichts dran ändern. Und
Mhm.
also das ist eigentlich so ein bisschen, was ich hauptsächlich in der Forschung mache, quasi. Du nimmst das Zeug als Input und ich möchte quasi Sachen ein bisschen ändern. Also ich nehme quasi diese exakten Formeln und mache damit und versuche damit Aussagen zu treffen über quasi nicht mehr exactly solvable Models.
Mhm.
Und sozusagen so wenig von diesen exakten Formeln als Input, um quasi möglichst viel Output
Mhm.
zu produzieren.
Ja, siehst du, ich bewege
Das
mich in eine
ist.
ganz andere Welt, wo es mehr oder weniger keine exakte Lösungen von irgendwas gibt. Das heißt, wir machen
Ja.
alles durch irgendwelche Approximationen und versuchen,
Mhm.
was rauszukitzeln.
Ja,
Deswegen bin ich immer nicht verwirrt, aber es ist für mich relativ unnaturell, explizite Lösungen und Systemen zu haben, weil
ja,
das kommt
ja,
bei
ja,
mir
klar.
nie vor.
Ne? Also wie gesagt, es ist immer so, es kommt ein bisschen drauf an. Also du hast halt viele Leute, die halt an wirklich diesen ganz exakten Lösungen arbeiten.
Mhm.
Aber man kann das eben quasi auch als Input nehmen und dadurch dann quasi diese Sachen als, okay, es ist eine Blackbox, dass es funktioniert. Aber ich nehme das und mache dann zum Beispiel Moderate Deviation Resultate für
Mhm.
Teilchensysteme. Und dann wird es wieder probabilistisch.
Mhm.
Also man kann diese Sachen auch kombinieren. Das
Ja, aber siehst du,
geht.
da fehlt mir einfach die Erfahrung, irgendwelche
Mhm.
analytische, sagen wir, Muster zu haben, um die ich dann bauen könnte.
Ja.
Das habe
Ja,
ich
aber das ist,
nie wirklich getan.
naja, das ist aber auch trickreich. Also das ist, geht eigentlich jetzt auch so ein bisschen, also da gibt es auch nicht so viele Resultate in die Richtung. Also es fängt jetzt so, also es nimmt ein bisschen mehr Fahrt auf, jetzt würde ich sagen.
Mhm.
Wird besser, aber ist immer noch nicht gut. Also im Sinne von, man kriegt jetzt langsam mal diese non-exactly solvable Sachen raus. Also man ist immer noch bei Modellen wie dem RCEP, also dass du nicht totally asymmetric, sondern nur asymmetric bist. Das ist immer noch so quasi, so quasi noch integrable.
Mhm.
Da gibt es Möglichkeiten, das Ding, auch wenn es selber nicht wirklich integrable ist, kann man es immer noch mit integrable Probability untersuchen. Und dann
Mhm.
kann man da quasi Resultate nehmen und dann quasi ein bisschen was damit basteln. Also, dass du zum Beispiel, also was ich jetzt mit Patrick, die Arbeit, wo wir gerade dran sind, ist quasi, das macht quasi Vergleichstechniken. Wenn du einen Ausschlussprozess hast mit offenen Rändern, dann sollte sich der eigentlich verhalten wie ein System mit auf den Integers. Und wir bekommen das raus. Also, dass man das wirklich vergleichen kann in einem gewissen Sinne.
Mhm.
Also, nimmt quasi auch sozusagen, okay, auf den Integers wissen wir alles über das System, das ist der Fullspace. Auf dem Halfspace weiß man mehr, aber nicht alles. Und wir haben quasi eine Technik jetzt, wo du sagst, okay, viele Resultate, die jetzt nicht mehr exakte Formeln sind, aber so Asymptotiken von deinen Last Passage Times, Last Deviation Sachen, sowas kriegen wir alles in den Griff. indem wir quasi sagen, okay, wir verstehen es auf einen Full Space und dann können wir das übersetzen auf einen Half Space. Zum Beispiel. Also das kriegen wir hin jetzt, aber das ist quasi forthcoming work.
Mhm.
Also dass man
Ihr
quasi
kriegt einfach irgendwelche Fehlerterme dann oder was?
genau, aber die können wir komplett quantifizieren. Also wir können quasi sagen, okay, du lässt das System laufen von quasi Full Space und Half Space und fragst dich, okay, was passiert lokal? Wenn ich da zum Beispiel interessiert bin, was machen die Teilchen? Und wir können quasi quantifizieren, wie lange du diese Systeme miteinander laufen lassen kannst.
Und ist das abhängig von wie nah am Rand du bist im Half-Space?
Genau, genau. Also natürlich wirst du Perturbations haben, die sich reinbewegen, aber wir kriegen für die Perturbations KPZ-Verhalten hin. Also wir kriegen hin, dass die Perturbations sich so verhalten wie, also dieses T hoch 2 Drittel ist da meistens. Also die Fluktuationen von der Geodäte ist quasi ja genau die Korrelationslänge und wir bekommen das hin. Also dass quasi diese Approximation sich, also dass quasi die
Mhm.
Störung sich so bewegt, so schnell wie sie sich bewegen sollte.
Mhm.
Also wir können quasi die Systeme miteinander koppeln. Also man kann schon ein bisschen was machen,
Und
aber es ist alles quasi Work in Progress.
nur jetzt aus Neugier, was für Kopplung macht ihr in diesen Sachen? Sind das fast sichere Kopplungen oder Kopplungen, die irgendwie nur mit höherer Wahrscheinlichkeit klappen?
With high probability. Also, ja. Also oftmals machst du sowas wie es gibt die kanonische Kopplung fürs Zeichensystem, wo du quasi sagst, okay, wenn ich ein System mit einem offenen Rand habe und einen Full Space, sage ich einfach, okay, ich versuche immer ein Teilchen reinzustecken in Knoten 1, wenn ich kann. Und beim anderen habe ich halt durch einen Full Space vorgegeben, okay, ich habe meinen Ausschlussprozess, der bewegt sich halt rüber. Und immer wenn ich quasi einen Knoten im System habe, wo quasi beide sind, dann versuche ich die gemeinsam zu bewegen, wenn ich kann, und wenn nicht, dann halt nicht. Und das Ding nennt man kanonische Kopplung. Und
Und
wenn du
die
quasi sagst,
hat irgendwelche hoffentlich exponentielle Apparate,
polynomiell in der
nur
Zeit.
polynomiell.
Also quasi, du hast ja das eine Störung.
Ja,
Eine Störung bewegt sich ja mit. Achso, sorry, wenn du exponentiell quasi meinst im Vergleich zum Expected Value. Wenn du eine Störung am Ursprung ansetzt, dann
ja.
wird sich diese Störung ausbreiten bis zur Zeit t von Größenordnung t hoch 2 Drittel.
Mhm.
Also quasi, wenn ich das System anschaue und ich schaue
Nee, und
quasi
was
in
ist
das.
deine Wahrscheinlichkeit? Okay, ich frage anders. M- Wenn du mehr als t hoch 2 Drittel weg von der Störung bist,
Ja,
was ist oder wie nah an eins ist deine Wahrscheinlichkeit, dass die zwei Systeme dort gekoppelt bleiben können?
wir bekommen Stretched Exponential. Aber man würde Exponential, oder man würde es sogar besser als Exponential erwarten in manchen Fällen.
Okay, so ihr habt besser als polynomiell dann.
Ja, ja. Wir haben aber quasi die Zeit, also was ich mit polynomiell meinte, ist also eine Störung bis zum Zeitpunkt t breitet sich quasi polynomiell in t aus.
Ja, ja,
Also
nee, nee.
und mehr kannst du
Ich
nicht
denke
erwarten.
hier immer Sachen, weißt du, weit weg von Ränder und so, wie gut kannst du Sachen
Ja.
gekoppelt.
Exponentiell, aber verwendet auch relativ viel Maschinerie aus quasi, die jetzt erst in den letzten 2 Jahren entwickelt wurde.
Okay.
Also viel Moderate Deviation Resultate für Perturbations, also für Second-Class Particles in dem Fall.
Mhm.
Nennt man das. Genau, also da sind wir. Aber wie gesagt, da passiert eine ganze Menge und wir haben jetzt mal diese Maschinerie da gemacht. Also zumindest halt mit der Idee, Mischungszeiten vom Ausschlussprozess zu analysieren. Und da
Mhm.
bekommen wir jetzt auch das KPZ-Verhalten. Also wirklich das n hoch 3 halbe.
Mhm.
Also n hoch 3 halbe ist quasi t hoch 2 Drittel. Wenn
Ja,
das
ja,
gleich
ja.
n sein soll, dann. Also es passiert einiges. Also es wird schon besser.
Hm.
Aber immer noch
Hast du
viel.
gesagt, kommst du zurück?
Äh, Ende,
Wann?
Anfang April komme ich zurück.
Nee, nee, für Weihnachten meine ich.
Ach so, Donnerstag.
So in 3 Tage.
Jo, 4 Tage. Also, ja.
Ah ja, okay, bei dir ist immer noch Vormittag.
Ja, Stimmt, bei mir fängt der Tag jetzt erst an. Ich gehe jetzt in aller Ruhe erstmal Mittagessen und
Also
dann.
bei mir ist jetzt schon fast Feierabend.
Jupp.
Oh Mensch, okay.
Passt.
Wie lange ist dein Flug?
8 Stunden. Also
Okay,
geht.
das geht noch.
Okay. Nee, also ehrlich gesagt, das Hin- und Herfliegen ist jetzt nicht so das Problem. Also kann man machen.
Kannst du direkt
Also,
fliegen oder musst du...
ja, nee, direkt. Also München, New York ist direkt.
Ja, nee, weil wenn ich zuletzt in New York war, musste ich durch Washington fliegen.
Wirklich?
Ja,
Okay. Wow. Nee, also ich habe nur Direktflüge. Also,
es hat nur eine extra Stunde gedauert,
aha.
aber wegen der Connection habe ich meinen Flug verpasst.
Okay, wow. Nee, also das sind eigentlich immer Direktflüge. Also München ist sehr gut angebunden.
Okay, ich habe aber aus Newark bin
Mhm.
aus New York,
Genau,
Newark.
ja, Newark. Aber
Wie spricht man das aus? Newark.
Newark.
Okay. Ja,
Ja, ist
ja,
ein bisschen,
ich hatte am Tag keine direkte Verbindung. Ich musste über
wow.
Washington.
Aber nach London oder wohin?
Nee, das war nach Frankfurt.
Okay, das wundert mich. Also ich kann dir sagen, es gibt täglich von München gibt es täglich 3 Flüge nach New
Nee, in die
York.
andere Richtung hatte ich eine direkte Verbindung. So,
Okay,
Frankfurt, Newark hatte ich eine. Das war alles mit, wie heißt das nochmal? Diese
United, oder?
American Airlines oder wie heißt die?
Okay, American? Ja.
Ja.
Also United fliegt
Ah, nee,
normalerweise.
Das war's, ja.
Ja,
United war.
genau.
Eine Richtung
Nee, aber
direkt, rückwärts musste ich über Washington.
dann hattest du aber Pech, weil normalerweise sind die verfügbar. Dann waren die vielleicht ausgebucht. Weil
Vielleicht.
normalerweise, also vor allem von München aus, da fliegt ein A380. Da kriegst du ja 700 Leute rein in das
Aber
Ding.
vergiss,
Also,
Frankfurt, nicht München.
aber Frankfurt fliegt, glaube ich, auch ein A380.
Keine Ahnung.
Also, wow.
War ein
Okay.
großes Flugzeug in beide Richtungen, aber
Aha.
ich musste rückwärts über Washington fliegen.
Okay, komisch. Also wie gesagt, normalerweise sind das immer.
Mhm.
Also ich habe jetzt eigentlich nie. Ich habe einmal, vor 3 Jahren, habe ich mal einen Flug über Amsterdam genommen, weil der halt deutlich günstiger war. Also das
Mhm.
hat halt dann die Hälfte gekostet. Und dann war ich so, okay, spare ich mir das Geld. Aber wirklich müssen, normalerweise, die Direktflüge sind am günstigsten und immer verfügbar. Also ich buche halt auch 3, 4 Monate
Es
im
kann sein,
Voraus.
dass es gab einen
Das
direkten
ist
Flug, der aber unglaublich teuer war oder so und
okay.
deswegen war
Ja,
es
ja, klar.
sofort außer der Frage.
Okay. Ja,
Aber ja, okay. Du kannst
ja,
direkt fliegen.
ja. Ja.
Gut, dann
Gut, ja.
Appetit.
Ja. Danke. Dir einen schönen Feierabend.
Schöne
Genau,
Ferien.
alles weitere. Ja, danke dir auch. Happy
Guten Rutsch.
Holidays. Ja, gleich. Dann sehen wir uns wahrscheinlich im neuen Jahr zur Besprechung. Das ist wahrscheinlich das
Ja,
nächste.
vermutlich. Hoffentlich soll es nicht schief laufen, weil die Woche bin ich in Berlin und ich komme
Mhm.
zurück am Donnerstag. Das heißt, es musste
Also,
wirklich
ja,
irgendwas Katastrophales
ja,
passieren,
ja.
dass ich am
Nee,
Freitag
nee.
nicht da bin.
Nee, nee, das geht schon.
Aber nur FYI, weißt du, wenn,
Mhm.
keine Ahnung,
Ja.
wegen irgendwelcher Verspätungen ich einen Tag später zurückkommen muss oder sowas.
Mhm. Ja, ja, klar.
äh,
Dann. Nee, nee, daran soll es nicht scheitern. Da finden wir auf jeden Fall was. Einen Termin.
Hoffentlich. Weißt du, weil
Okay.
ich komme zurück Donnerstag spät Nachmittag, Abend. Und wenn irgendwas da schief läuft, dann ist automatisch Freitagmorgen und dann könnte alles
Nee,
genau
nee,
knapp.
klar, aber ich glaub's nicht. Also
Ja, ich auch nicht,
normalerweise,
aber
du
nur.
kommst da schon an. Also die Deutsche Bahn es kommt drauf an, wie spät in der
Ah,
Nacht
nee,
du
nee,
ankommst, aber du
ist
kommst an.
Berlin, das heißt, ich muss nur aus Berlin nach Brandenburg Flughafen kommen. Das schaffe ich.
Ja, ja, das geht. Nee, nee, du kommst irgendwie raus. Also aus Berlin irgendwie.
Nee, nee,
äh,
ich glaube, wenn es irgendwas Größeres wäre, ich weiß nicht, Unwetter oder so,
Ja, 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 nee, nee, klar, das ist höhere Gewalt, aber ich denke mal nicht. Also,
aber
das
ansonsten
sollte schon gehen.
soll ich problemlos
Ja,
es schaffen.
ja, passt. Gut.
Du reist nicht an der Woche, oder?
Am Montag. Also am Montag fliege
Okay,
ich halt
so
nach
du
New
bist
York.
dann
Ja,
garantiert
ja,
schon
ja, ja.
in New York.
Genau. Ich bin dann wieder zurück im Rhythmus. Also, das
Gut.
passt. Gut, dann,
Dann, ja, okay, was
ja,
habe ich gesagt? Ich muss YouTube, Webseite vorbereiten und dann die E-Mail an Luisa und Roger schicken.
genau. Und sobald ich das mit Ben und Volker habe und Violette und Alessandra schreibe ich dann auch noch äh, an. Also
Ja, ich
fürs nächste
werde die
Abstract.
Sachen für Ben und Volker schon verschieben, aber ohne Abstract, weil wir haben es noch nicht.
Klar.
Okay, gut.
Gut, passt. Dann, ja.
Dann